Okay, we take the second question. That should be question number 4. It says that the reaction y going to the product is a first order with the is a first order with sorry with the initial concentration of y equals to with the initial concentration of y being equals to 0.55 times 10 to the power minus 3 mole per dm cube, and the rate constant is 5.25 times 10 to the power minus 3 per second. If it's clear, then what is the half-life of the reaction? The question is, what is the half-life of the reaction? So the solution, sorry, so we're given a reaction where y goes to a product. Y is not specified, the product is not specified, and the reaction is a first order. So a first order, in the reaction kinetics, we have different orders of reactions, and like a zero order, first order, second order, and so on and so forth. So we have what we call such. Then this reaction is specified to the first order, and the first order reaction has its rate equation. The rate of the first order reaction is mathematically expressed as a rate constant multiplied by the concentration of the reactant. In this case, the reactant is Y. Multiplied by the concentration of the reactant, the raised to power 1. That is what makes it a first order reaction. If it were a second order reaction has the rate looks like this. The K, then the concentration, let's say the reactant is A, will be raised to the power of 2. This is second order. Third order will be raised to the power of 0. So the first order is just to the power of 1. So in this case, in place of A, we are writing Y because Y is the reactant we have here. So it means for a first order, if this reaction is a first order, it means its rate equation is expressed as this. The rate constant multiplied by its concentration raised to the power 1. Then raised to the power 1, the 1 can still be eliminated. So this is how the rate equation of a first order reaction. Rate equation of a first order reaction. And if another way of expressing this equation is for rate, the rate of a reaction is expressed as the change in the concentration of the reactant with change in time. Then it usually goes with a negative if it is expressed in terms of the reactant. So if I'm expressing the rate in terms of the product, like we could say dp, let's say the product is p, you can say dp dt. In that case, we don't need to put negative because it is in terms of the product. If it is in terms of the reactant, you have to put negative, and this negative indicates that as the reaction goes on, the quantity of the reaction, the concentration of the reactants is decreasing, of course. So because reaction is the reactant species, they get disappeared and why the product species get formed. So which means if you are starting with like let's say 30 quantities of Y, and because of the reaction, it will be the quantity, which in this case the concentration of Y will be decreasing, while as product is being formed, the concentration of the product is filling up. So that's what the negative stands for. If you're writing it in terms of the of the reactant, supposing our product is P, if you want to write this rate in terms of the product, we would have said just the P, the T, the change in the concentration of the product over, sorry, the CP, the change in the concentration of the product over that of, over time without negative. So, but we want to do it in terms of why, since the information we have here is all about the reactant, not the product. So, if this is equivalent to this, it implies that we can, in place of this, write the the concentration, the Cy, the T, equals to KCy. So we can write this, and this is the equation that we're going to use to solve this question. And what we know is we are given the rate constant. The rate constant K we are given, then we are given the initial concentration of Y. Initial concentration of Y, which we will write as CYO. That is the original, the initial concentration. The not O here means the first concentration. The concentration at time t equals to 0. It is the initial concentration is given as 0.5 plus 10 to the power minus 3. Understand? So any other concentration it will have. So the question asks what is the half-life of the reaction? What does this mean? The half-life of a reaction is the time it takes half of the original amount of the reactant to disappear. So if the original concentration of Y is 3.5, 3.55 times 3.3, then its concentration at a time t, or at a time t a half, which is the half-life. So its final concentration is Cy. But in this case, if I to determine the half-life, it means the time at which this initial concentration would have what halved, which means it will be a half of this. So the concentration at that half of this is, we call it Cy. So, and it will give us from here it should give us 0.55 by 2. Alright, 0.55 negative 3 by 2. So this one will give us 1.775 times 10 to the power minus 3. So this is half of the original concentration. Now the question now is, what time will it take the concentration, the reactions to consume half of the original concentration? So the time it takes for the concentration to change from CYO to Cy, that is from this to half of its original, that is half-life. So that half-life is a time. It's a time. So to differentiate this from the normal time of reaction, we can write T subscribe to 1/2 as the half-life. So now, how do we now put all this into this equation to get the value for time? If you look at the equation, we have it's a differential equation having the Cy, the Ct. So we have to, what I call it, solve it. So by integrating it into a form that we can substitute for this. So this is taking us into integration. So this is why math is also very important. So let's see how we do that. Mind you, we are finding a t. T is what we are finding, but this time around, it's not just the time of the reaction, but the time for half of the original concentration to have reacted. So like I said, we have to solve this. Solving the differential equation. what is the differential equation? The cy dt equals kcy. So how do we solve it? So you might not be privy of integration and differentiation, but if I had to do this, then what we're going to do is we do variable separable. I will call it this the cy. We bring together the terms in concentration, the concentration terms, and together the other term, the time terms. So by dividing both out by cy, we're going to get this, and by we're going to get dt. So that is, we try to bring cy under here, then we take dt to this side. So if we do that, this should be k dt rather. So then we go further to integrate both sides. You understand? Integrating. If I integrating, so what we have? So if I'm integrating, then it means we are integrating this side, and we're also integrating this side. So by law of integration, this negative one will come out. So k is a constant. Every constant will come out of the integral. So by law of integration, the integral of 1 over s, the integral of 1 over s dx is what? Ln s. So if that is the case, then it means the integral of 1 over cy, the cy will be what? Ln ln of cy. Then we have a negative here, we must not forget. So, but this integration, we are going to do it between the initial concentration to this concentration, to the final concentration. You understand? Then the same thing, this will now be from time t equals to 0 to the time, a certain time, which is the half-life. So that is the case. It means after integrating this, then we will have to evaluate it at this limit given to us. Then equals to, for the t, we're going to have k into t a half. No, still not. So we can just say, okay, let us forget about this confusion. We can just say this is t. So if you get t evaluated between 0 and t a half, it is like substituting in place of t, put t a half, then minus, then t, in place of t we put 0. So which means we'll still end up having kt subscript a half, which is the half-life we are finding. So if this is the case, so how do you evaluate this one? We say we substitute this, that is negative ln cy, substitute cy for cy, which will still give us negative ln cy. Then minus, when we substitute cy for cy, then we're going to have minus ln cy naught. Understand? So this will be equals to k t a half. So this one will now be minus plus minus is plus, so which means we can write this as ln cyo minus ln cy equals to kt. Understand? So what we now do is to, sorry, I'm cleaning this, is to say t a half divided by k, giving us ln of cy naught minus ln of cy all over k. So we can now substitute. So from what we had, the initial concentration was 3 watts. I've just cleaned it. Sorry, looking for it. Okay, 3.55 times 10 raised to the power. That means lane of 3.55 times 10 to the power minus 3. Then minus lane of Cy, which is the half of the concentration, like we said, is 1.775 times 10 to the power minus 3. Then everything divided by the rate constant P, which is also given as 5.25 times 10 to the power minus 3. So substituting will give us lane of 3.55 negative super negative 3 gives us uh, okay, so that one gives us negative 5.641, then minus the lane of lane. I actually have the lane button here, you can press it. Lane of 1775 raised to the power negative 3 gives negative 6.334, negative 6.334. Everything over 5.25 times 10 to the power minus 3. So negative times negative will become positive, which means we are going to say minus 5.641 plus 6.334. That will give us positive 0.693. 0.693. So coming back here, we're going to have 0.693 up divided by 5.25 times 10 to the power minus 3. So this will not give us 5.25 minus 3 to give us 132. 132. So you can now say therefore our T, mind you, all this is T a half, which is the half life. Therefore our half life is what? 132 seconds. So which is the answer. So the question really looks tough, looks long, especially if you're not privy to integration and differentiation. Well, in shortcut, I'll give you in case you come across a similar question for a first order reaction. Then, if you have to find the half life of a reaction, the first order reaction, the half life, simply use this formula. The half life will be 0.693 all over the rate constant, just like what we got here. So the whole of this will summarize into this. So if you can remember this formula, once you have to determine the half-life for a first order reaction, not just for all other, for a first order reaction. Forget about all the concentrations they give, the initial concentration. Just go straight to dividing 0.693 by the given rate constant. So you get the answer straight. But if you are to show the calculations, this is the step you have gone through. This is the procedure. So I hope that is understood. If understood, then we should go to question 5. Question 5 says given the half cell reaction, given the half cell reaction. So what did they give? Given the half cell reaction, 2Br going to Br2. 2Br going to Br2. How many moles of electron will be required to produce 0.5 cgm cube of bromine at STP? How many moles of electron are required to produce 0.5 cgm cube of bromine at STP? That is a standard temperature and pressure, and they give you that the molar volume is equals to 2.4 dm cube. So let's look at the question. We are given the half cell reaction. Why is it called half cell reaction? This reaction is actually there should be negative here. They did not give it. So in analytic chemical cells, where we have a bromide ion being discharged into bromine gas, then this is half of the electrolytic reactions there. Of course, this will occur at the anodes, and this is what we have. We have a similar equation happening at the cathode, which is the cathodic half equation. This one is the anodic half equation. So we have to determine how many moles of electron we need, because for us to discharge this equation is not a complete equation. For it to be a complete ionic equation, we have to indicate why electron is lost or gained. So in the solution, for instance, for us to have bromine formed from a bromide in the solution, then it has to be like this. From a bromide to a bromine, so it means you have to in balancing, you have to have 2 here. Then for the charge, this is -2 and the charge is 0 here. So the charge has to be balanced, and that is by putting -2 here as well, like we saw in example 1. So this reaction will occur at the anode. The negative ion has to lose electron to become discharged. So this is the balanced ionic equation for that. So the question is, how many moles of electron are required to produce 0.5 mole of bromine at STP? So it is simple from here that we need 2 moles. This is 2 moles of electron. We need 2 moles of electron. Understand? To get 1 mole of what? Bromine. That is from the equation. Now, before we could tell how many moles of electron we give 0.56 cube. But what we have from this is this. Another implication of this is that 1 mole of bromine, as a bromine gas, then 1 mole of it should have a volume equals to 22.4 dm cube, which is the molar volume. Molar volume is the volume of 1 mole of a gas, is 22.4 dm cube. So what am I saying? That 1 mole of bromine as a gas has a volume equals to 2.4 dm cube. So if that is the case, it now means that 2 moles of electron is giving 22.4 dm cube of bromine. That is, instead of writing the mole, so we are writing the volume, because the question is asking us how much mole will produce this volume. And what we have from here is that 2 moles of electron will give us this volume. So this is the volume equivalent of 1 mole of the gas. So which means what we go back to say is, from here, another way of rewriting this now is that this implies that, okay, or implying that 2 moles of electron produces 1 mole of bromine, which is in terms of volume 22.4 dm cube of bromine gas, because this is the volume of 1 mole of a gas as stated. Now, the question now is how many moles of electron now? Let's call that S moles of electron will now produce 0.56 dm cube. So this S is going to be our answer. So like you are used to doing, you multiply S by this, you multiply this by this. So doing that, you are going to have 2.4 S, and 2 times this, you're going to have 2 times 0.56. So dividing both sides by this, will give us the most. That's 2 times 0.56, well, 2.4. So it gives us 0.05, 0.05 mole. And this is the answer of electrons. So that's the answer. So the question is simple, it's just a simple relation. So you have to first write a balanced ionic equation that gives the half equation. You have to write the balanced half equation that gives this bromine. Then from here we can say that 2 electrons, 2 moles of electron gives 1 mole of this. But because we want to work in volume, then 1 mole of the gas has a volume of 24 dm cube. So then this is our basis. Then we now want to know how many moles, 2 moles of electron will give this volume, this molar volume. Then how many moles of the same of electron will now be required to give the volume in the question. So do what cross multiplication. This multiplied by this equals to this multiplied by this. Then we have to by this and get to answer. It's as simple as that.